Alright, what we're looking at is a Mathematica program to run the stochastic funnel algorithm and then use a Newton search to find the optimal parameter estimates for a nonlinear model. The nonlinear model that we're using is the RAT43 model. So we'll evaluate the notebook. Alright, this does the stochastic funnel algorithm 100 times, and what we're looking at is the first time we ran the stochastic funnel algorithm, 247 generations until termination. The second time we ran it, 3 generations. Alright, I'm going to pause it now because it's up to 100 generations, and we'll come back. Back again. Now we're up to 61 runs of the stochastic funnel algorithm. Pause it again, come back after 100 runs. Alright, we've completed 100 runs of the stochastic funnel algorithm. Now if we go back up to the top of the program, we can see here's the data. We're calculating the sum of squares error for the data. We're using a log 10 scale because it goes over quite some orders of magnitude. We create a table of parameter table space for parameter values. We've got beta 1, beta 2, beta 3, beta 4, and we've got the SSE. So we're making a table, 100 entries, and we're filling it with zeros for each one of these things. Alright, termination criteria. This is the maximum divided by the minimum of the SSE and beta 1 and beta 2 and beta 3 and beta 4, and all of them have to be smaller than 1.01 in this case. Relaxation, dynamic relaxation, we've set it at 0.01, and static relaxation 0.01. Dynamic relaxation helps to mitigate the issue of premature convergence. Static relaxation also mitigates the issue of premature convergence, but it looks after the stochastic funnel algorithm later in a run, whereas dynamic relaxation modifies the search space throughout the course of the run. Alright, so here we go. So let's start looking at the data, or the output from this. So what we've found from the last run is that the log of the SSE is 3.94381, and these are the parameter estimates of beta 1, beta 2, beta 3 and beta 4. We can look at correlation plots of the different parameters, pairs of the different parameters for those 100 runs, and what we see is that there's some shape to the SSE. Got histograms here, and here we've got the SSE histogram. Most of the values of the 100 SSE values are relatively small, but some are up around the million size. Number of generations to termination, well, between 20 and 30 seems to be about the average, or 20 and 40, about the average. Beta 1 histogram, the optimal value for beta 1 is 699, so we're certainly in that ballpark. Beta 2, the optimal value is 5.26, pretty small. Beta 3, optimal value is 0.76, bit hard to see it on this scale, but it's down there. And beta 4, 1.27 down there. So these, if we look now at these plots of the best 20, so here's beta 1, beta 2. So beta 1 699, which is about here, and beta 2 5.26, which is about here. So our plot incorporates the region where the best of those two estimates are. Beta 1 and beta 3, beta 1 699, beta 3 0.75, so 0.75 is in here, so it's in that plot. Beta 1, beta 4 is 1.27, so 1.27 is here. It's the optimal values are within the page of that plot. We see that there's correlation between beta 2 and beta 3. Alright. We go down here. Here's the data, and in red is the least squares model, and it's a pretty good fit. Here we've got find minimum, and we've got a step monitor, and it starts from the best values for beta 1, 2, 3 and 4. These are from the last run of the stochastic funnel algorithm. That's run 100. Alright, so here are the values that we've got, and this is the SSE 9144, so we want 8786, and that took, I don't know, 30 steps. Alright, 30 steps to get to the optimal solution. Alright, here are some plots, contour plots for the various parameter pairs that make up the 4 parameters of the RAT43 model. And what we see is that there is a minimum in the region that we're in the region where we found answers, and there's no other minimums around there. This plot here, this shows a plot of the best fit, 95 and 99% confidence intervals for the model. Here's the model, and here's some of the parameters that we use. So beta 1, beta 2, beta 3 and beta 4. Here's a standard error. Alright, t statistics for each parameter and p-values. What we see here is the p-value for beta 4 is nearly 0.09. So at the 5% significant or 95% confidence interval, it's not a goer. So we might consider redoing the fitting process with just a 3-parameter model. Analysis of variance table. Here's the sum of squares error for our final model. Uncorrected total sum of squares error and corrected total sum of squares error. Correlation table. We see here beta 2, beta 3, beta 2, beta 4, beta 3, beta 4. Significant correlation there. Alright, well, that's all we can do. We found the optimal parameter estimates.